Hello everyone. Today we're on tutorial 6, first year university physics, momentum. Okay, let's go to my notes. Okay, essentially we're going to summarize some formulas from the chapter that you're going to need, plus some of the ideas that you will need. The first thing is the definition of impulse. Force multiplied by time is the impulse, and the formula is that the change of momentum is equal to the impulse. It's derived starting from Newton's second law and the definition of acceleration. I think I'll do this on the whiteboard for you. Right, impulse. Force multiplied by time. So we start with Newton's second law. Define the acceleration, final velocity minus initial velocity divided by time. This formula will be exact if acceleration is constant. If it isn't constant and it varies, then this will give you the average acceleration. Either way, the formula for the impulse will be the same. So if I call this 1 and this one 2, then substituting 2 into 1, I get force equals mass, and push this in there. Take time across the equal sign, so it's Ft, expand the brackets, mvf minus mvi. So this then is my important formula for the impulse. Force multiplied by time is equal to the final momentum minus the initial momentum. Okay, let's go back to the notes. Okay, the next thing is a conservation of momentum. This is very important. I'm going to come back to add a few details to this. Conservation of momentum. Total momentum of an isolated system is constant. And we're going to use it in the form of momentum before collision equals momentum after collision. Now there are two kinds of collision. There's elastic collisions and inelastic collisions. In an inelastic collision, kinetic energy is lost or is not conserved. Momentum is conserved. In an elastic collision, kinetic energy is conserved and momentum is conserved. So in both cases, momentum is conserved, but in elastic collisions, kinetic energy is not conserved. Elastic collisions, kinetic energy is conserved. I'm going to expand on this a bit as well on the next pages, but let me first define the center of mass. We take an object that can be any shape, and we want to find its center of mass. First of all, we choose an origin, and this can be drawn anywhere. Once you've chosen the origin, we measure the distance of particles from the origin. We're thinking of the object as made up of lots and lots and lots of small particles of mass m1, m2, mi, up to a big number, mn. Now, wherever I draw my origin, I'll end up with the same position for the center of mass. The numbers will be different because they'll be measured according to the origin that you've chosen. So if I choose an origin here, my distance from the origin is r1, which I can think of as a position vector. My distance of m2 is r2. My distance of a general mass is mi, it's a distance ri. In order to get the definition of the x component of the center of mass and the y component of the center of mass, I resolve r into the vertical and horizontal components. So here I've got x1, y1, x2. This x2 is this one here, y2. So if I take all my x's, m1, x1 plus m2, x2 plus all the way up to largest very big number n, mnxn, divided by m1 plus m2 up to mn. This is just the total mass. So my x component of the position of the center of mass is given by these products divided by the total mass. Similarly, the y component of the center of mass is given by multiplying all the y components by the mass, m1, y1 plus m2, y2 plus ... plus up to the big number n, divided by the sum of the masses, which gives me the total mass. This defines my center of mass coordinates and tells me exactly where on the object the center of mass is. I emphasize again, if you choose the origin somewhere different, these numbers will be different, but the position of the center of mass will be the same, whichever way you calculate, from whichever origin you choose. Let me expand then on this number 3. In collisions in which one object embeds in another, kinetic energy is not conserved, but momentum is conserved. Hence, only use conservation of momentum, not conservation of energy, in problems involving embedding. There are other examples which I'm going to go through on the whiteboard, and I'll include this one as well. More generally then, what we said before, in elastic collisions, kinetic energy and momentum are conserved. In inelastic collisions, kinetic energy is not conserved, but momentum is conserved. So let's go to the whiteboard and see what kind of collisions are elastic and which ones are not elastic. Elastic collisions. Here, both kinetic energy and momentum are conserved. A typical example is when you have very hard balls, billiard balls or snooker balls, for example. We suppose, for simplicity, UB equals 0. UA has got some velocity. They hit each other, A, B, and then they shoot off in some direction. We suppose this is ball B, and ball A shoots off in this direction, with final velocity VA and final velocity VB. This is angle phi, this is angle theta. When the balls are very hard, they hit each other without loss of KE. So we have both conservation of kinetic energy and momentum. One more special case of hard balls colliding, and that is head-on collisions. Again, energy and kinetic energy and momentum are conserved. We have a ball A and a ball B. Again, I suppose UB equals 0. Excuse me. And UA is in some direction. In this case, if they hit each other head-on, then the motion after collision will be along the horizontal. The chances are that ball A will bounce off ball B, and so its direction after collision, VA, will be opposite that of B, VB. So this is after collision. So in a special case of head-on collisions then, they won't fly off at an angle, but they will remain in the linear direction, in this case the horizontal direction, with the chances that the moving ball bounces off the stationary ball. Okay, so this is before collision. And this one is after collision. Okay, next we consider inelastic collisions. It's in order so you can recognize when a collision is inelastic. Keep in mind, momentum is conserved. But kinetic energy is not. What kind of examples? Supposing you have two pieces of clay. Now we throw one piece at another piece of clay. Before collision, after collision. With soft things like clay or plasticine or whatever, the objects tend to stick together. Even if they move along and separate a little bit, the fact they've stuck together even for a short time, they may stay stuck together, or they may stick a little bit, and then they may even separate and go off in other directions. Either way, energy is not conserved. So when two soft objects, sticky objects, hit each other, energy is not conserved. Kinetic energy is not conserved, but momentum is conserved. Another example is when objects embed themselves, or when one object passes through another object. I'm thinking here of blocks of wood or concrete. Supposing you shoot a bullet through, say, a block of wood, concrete, whatever it is, it doesn't matter. Now the bullet, this is before collision. Now after collision, you may get the bullet embedding, or you may even get the bullet passing through. Either way, this is an inelastic collision. Can you imagine as the bullet hits the block, it tears the bonds making up the wooden block. So you have a lot of friction, a lot of heat is given out. In other words, a lot of kinetic energy is lost. Similarly, for the bullet to pass through, it's breaking up the bonds in the wooden block. A lot of heat is generated. Essentially, it's frictional forces acting to generate the heat. So again, a lot of kinetic energy is lost. And so this collision is inelastic. Of course, if you take the total energy into account and take all the heat lost and all the energy lost to friction, then you will have conservation of energy. So overall, energy will be conserved. But the kinetic energy in such a collision is not. So this collision is inelastic. I'll do one more example of an inelastic condition, which is important. So let me erase all of this. Supposing, and this is similar to one of your tutorial questions. Supposing I have a bomb. It can be a nuclear bomb, a chemical bomb, any kind of bomb. You can see, let's imagine this thing is stationary. So the kinetic energy before collision is 0. Now the bomb explodes. There can be some kind of chemical reaction or whatever happens. But the chemical energy, or if it's a nuclear bomb, the nuclear energy gets converted into kinetic energy. So the thing explodes, and then the fragments of the bomb fly everywhere. So you can see there's K here, there's K here, and there's K here. So when you add up all these kinetic energies, the kinetic energies may be very large. So it's very different to zero. Of course, the kinetic energies have come from the chemical reactions making the bomb explode, or the nuclear reactions making the bomb explode. So overall energy is still conserved, but kinetic energy is not. So a bomb exploding is an example of an inelastic collision. So let me stop sharing, go back to my notes. Right, the next thing, oh yes, objects bouncing off walls. Let me read this for you and I'll explain. Problems involving collisions with fixed objects are problems to do with impulse. Remember the formula for impulse at the beginning? This is where you use impulse, when an object bounces off a fixed object, like a ball bouncing from a wall. The wall is a fixed object and the ball bounces off it. Neither kinetic energy nor momentum is conserved by the movable object alone. The missing energy and momentum goes into the fixed object so that overall energy and momentum is conserved. However, we cannot use the principle of conservation of energy and momentum to calculate in such problems because there is no simple way to calculate the momentum and/or energy of the fixed object. We can only do calculations involving the movable object. Therefore, in such problems, you should use the impulse formula. Should be an E there. Force times time is equal to the change in momentum. An exception when momentum is conserved is when the initial velocity is equal to the final velocity. Here, this is equivalent to saying the coefficient of restitution is equal to 1. Now, the coefficient of restitution measures whether a collision is elastic or not even. Here, even energy will be conserved. If the initial velocity is equal to the final velocity, even energy is conserved. And the coefficient of restitution measures whether an object is elastic or not. If the coefficient of restitution is 1, you have an elastic collision. The velocity after is equal to the velocity before. And the coefficient of restitution, notice, is defined as the final velocity divided by the initial velocity. And you can see, depending on the value of epsilon, it tells you how inelastic a collision is. The lower the coefficient of restitution, this is the Greek letter epsilon, the lower the coefficient of restitution, the more inelastic the collision is. So here I've given you some examples. This is the one I did on the whiteboard. Kinetic energy conserved, momentum conserved. When you have embedding or a bullet passing through, an object passing through, or clay sticking together, these are inelastic collisions. When you have bouncing off, when the velocities are different, you can't use conservation of energy and momentum anymore. You have to use the formula for impulse. So all of these kind of problems, except when VI is equal to VF, you need to use the formula for the impulse. Number 6, Newton's universal law of gravitation. This is force is equal to the gravitational constant, the universal gravitational constant, or Newton's gravitational constant. The product of the two masses divided by r squared. So even if you have two masses on Earth, two small masses, there is an attractive force between them. There's an attractive force between all masses. But the gravitational force is very tiny for small objects. But for an object the size of the Earth, the gravitational force is quite large. And in fact, that's why we stick to the ground. So we need to be grateful for gravity. Now we can use this formula to obtain a formula for gravity in terms of the gravitational constant, the mass of the Earth, and the radius of the Earth. I think I'll do this on the whiteboard for you. Newton's law of gravitation. Let's consider two masses, big M, little m, separated by a distance r. The gravitational force is always attractive and is given by Newton's law of gravitation. The force is proportional to the product of the masses divided by their distance, their separation distance squared. The constant of proportionality, G, is called the universal constant, universal gravitational constant, or Newton's gravitational constant. So this then is my Newton's law of gravitation. Even with small objects, they still attract each other. But on Earth, with small objects, you don't see them being pulled together because the gravitational force is a very tiny force. So for ordinary masses, the gravitational force is absolutely negligible. But for a mass the size of the Earth, the force is quite large. And in fact, this is why we stick to the Earth, because of gravity, thankfully. Let me do a proof of a formula for acceleration due to gravity in terms of G, the mass of the Earth, and the radius of the Earth. So let me consider the Earth then. Let me rub out that little bit. This is the radius of my Earth. I consider an object close to the Earth at a height h. My acceleration due to gravity is ag. Now ag will vary according to the height, but for distances close to the surface of the Earth, to a good approximation, the acceleration due to gravity is constant. If you go tens of miles away from the Earth, you start to notice that g will diminish. From Newton's law of gravitation, the gravitational force decreases as you move away, and so does the acceleration due to gravity. But close to the Earth, to a good approximation, we can take the acceleration due to gravity to be g. We can also approximate if an object is just above the Earth at a small height. The radius of the Earth is quite huge, so a small height, a few meters, 10 meters, 30 meters, is very small. So to a good approximation, we can approximate all of this by the radius of the Earth. Now, my force by Newton's second law is given by mg. So I'm going to substitute into my Newton's law of gravitation. So I have g, the mass of the Earth, and let's suppose that my mass of the object is little m. Then my approximation is the radius of the Earth, so this is r squared. The little m's cancel. So I have my formula for the acceleration due to gravity close to the Earth's surface. In terms of Newton's gravitational constant, the mass of the Earth, and the radius of the Earth. Okay, I'll go to the notes. We come to our final but very important item, conservation of momentum in separate orthogonal directions. Many calculations are greatly simplified by the following very important observation. Momentum is separately conserved in two orthogonal directions, e.g. the x and y directions. This was an observation made by Newton, which enabled these calculations to be greatly simplified. I might mention that your laws of mechanics come from Newton's book around about 1680. I can't remember the exact date. The book was called Philosophia Naturalis Principia Mathematica. It was in this book that Newton stated his famous laws and did many, many calculations on tides and all sorts of things. Really quite incredible calculations. And he used calculus for the first time. He was amongst the first to use calculus. He's, in fact, one of the inventors of calculus. The other one was Leibniz in Europe. But it's an amazing book that can be obtained in these Dover editions. Difficult to read, however. It's basically written in Latin. Years ago, when I was at Oxford University, we had a talk by a certain Nobel Prize-winning professor, Professor Chandrasekhar. He won the Nobel Prize for work on neutron stars. He was about 80 years old at that time. This was about 1992. And he was writing a book, translating Newton's book, which is written in Latin and written only in words, not in modern mathematical notation that we use today, which greatly simplifies calculations. So in his book, Professor Chandrasekhar translated Newton's kind of word thinking, his logic in words, in modern mathematical language. And he started out his talk by saying that compared to Newton, I am a dimwit. And this is a Nobel Prize winner. So imagine how brilliant Newton is regarded. Okay, I'll stop there.